let's take a look at example 5.46 here. The giant swing at a county fair consists of vertical central shafts with a number of horizontal arms attached to its upper end. Each arm supports a seat suspended from a circle 5 meters long, the upper end of the cable being fastened to an arm that at a point 3 meters from the central shaft. Find the time of one revolution of the swing if the cable supporting the seat makes an angle of 30 degrees with the vertical. And then B, does the angle depend on the weight of the passenger for the given rate of revolutions? Okay, so I want to first find the period, the time for one revolution. So I'm trying to find period. Now I do have to be kind of careful here. We are going to have a cable that has tension in it, capital T, and we're trying to find capital T period. So we'll just have to be a little careful on that. All right, so first thing to note is this is in circular motion. So you go, okay, circular motion. So now I need to sum up the forces parallel to the radius and set it equal to MAC. The reason I want to do this is because inside of AC, which is V squared over R, and inside of V is 2 pi R divided by the period. That is the value I'm looking for. So this is how I'm going to get to it. Here, I'm going to need to draw a free body diagram. So whenever we use this, we have to have a free body diagram that identifies the direction of AC and makes it positive. So this is the center of my rotation. I will also need to know what is the radius for doing this R value here. All right, to find this radius, we're going to have to do the 3 meters plus, we got this little triangle here. So this side down here is what? 5 times the sine of 30. So the radius comes out to be, what, 2.5 plus 3, so this is 5.5 meters for my radius. All right, let's finish this free body diagram that we got distracted from there. So I got mg, and I have tension. Okay, so a portion of that tension is acting radially inward, so that'll be tension cosine of, in this case, 60 degrees. So I have tension cosine of 60 equals MAC, which I'll make my substitution V squared over R right away. In the Y direction here, the sum of the forces in the Y direction is going to be 0. They're not changing their angle, it's a constant angle there. So I have tension sine of 60 minus mg equals 0. The reason we need this is I don't know what the tension is, so I want to get it out of that equation. So I can do tension is equal to mg divided by the sine of 60. All right, so now I have mg cosine of 60 divided by sine of 60 equals m times v squared, which is now 4 pi squared r over t squared, and then we're still having r in the bottom to cross out with that r squared. Fantastic. Now the first thing I'm going to do here, simplify it a little bit. So I see that the masses cancel, so does the weight of the passenger affect the angle? No, it should be the same. All right. I have sine and cosine, so this is going to be g divided by the tangent of 60. If I would have used 30 over here, the tangent would be on top because this side would be sine and that side would be cosine. So if we wanted to, we could make that change there if we needed to. So 4 pi squared r over t squared. Solving for t, the period, so I'm going to get the square root of 4 pi squared r times the tangent of 60, all divided by g. Again, does not depend on the mass. All it depends on is that r value that we found earlier and the angle. As you change that angle, that changes the period as well. And so we end up plugging this in and getting something like 6.19 seconds. So that is our part A. And again, for part B, since the mass canceled out, the weight does not matter. There you go.